Okay, if not, let's dive into our topic today. So today I'm very excited to start uh, statistical mechanics. So, so far we have been doing a review of classical thermodynamics, and I enjoyed it very much. But our topic is statistical mechanics. So, what is statistical mechanics? So, statistical mechanics is the science. So, it is the science, or it's also an art, really, of turning uh, microscopic physical laws or into macroscopic statements or laws of some extensive system. Okay, so this is not very rigorous, and I'm not going to um, aim for too much rigor. By the way, this part of this lecture is heavily based on David Tong's lecture notes. So if you want, he actually does a very good job of discussing a lot of nuances. I have cut down on some of the nuances because a lot of the nuances that he talks about has to do with quantum mechanics. And he's very, very careful to make things rigorous. So, but I'm just not going to go so much into that. So, for example, a typical everyday system. So, if I take a typical everyday system, so it could be, say, the number of gas molecules in a room, in an average room, or number of molecules, say, in a bar of magnet. Uh, you know, so they have typically something like 10 to the power 23, particles, okay, or molecules. So that's a lot of particles. I mean, that is like humongous, right? I mean, that's a large, large number. So now, if I so at some level, they all these particles follow some sort of equation. It could be the Schrodinger equation, or if you can approximate the situation by Newtonian physics, it could be Newton's laws. So So you'd think that, to say anything about the macroscopic nature of the system, you'd have to solve, say, a coupled Schrodinger equation for 10 to the power 23 particles, right? That's not going to be very, very practical, okay? This is not going to be. If you have done any quantum mechanics, you know that solving a Schrodinger equation for two particles is hard enough. In fact, solving the Schrodinger equation for one particle, if the potential is kind of funky, is hard enough. And but but if the but for two particles, if the potential is generated by their interaction, is hard enough. And for three particles, we have to resort to numerics. So, hey, can you just can I take a few minutes break? I think there is some sort of delivery that is happening. So can you give me like 3 minutes break? Sorry about that.
Okay, sir.
Yes,
Yeah,
sir.
sorry.
Yes, sir, sure.
Sorry about that. All right. Can you guys hear me?
Yes, sir.
Yes, sir.
Okay, good. Awesome. Yeah, so it's not very practical to solve these. And not only is it practical, it's actually not even desirable, right? So suppose, by some very unlikely miracle, we find the wave function that describes 10 to the power 23 particles. It will be so complicated that we won't be able to get any useful information out of it. Okay, so I think Mehrdad is here. Let me just make sure. All right, so yeah, we won't even be able to. So that's basically, that's not the way to the way to understand these systems is not to solve all those equations by brute force. The way to understand them is to actually take into account their quantum nature. We have to understand, what the nature of the quantum particles are. We don't have to understand and then apply ideas of statistics. Okay, and so the other thing is that we also need to understand that the physical quantities of interest are different at different scales. So for example, the idea of temperature for a single electron doesn't make sense, okay? So similarly, the idea of spin, which is a quantum mechanical idea, usually doesn't have relevance for macroscopic systems. Okay. I mean, angular momentum does, but spin doesn't. Okay. So, so another way to express the same idea is to say that more is different, meaning that the more particles you have doesn't mean that you're solving the same equation more and more times, but that a new reality emerges at a different length scale, okay? So a new kind of reality emerges. So this emergence of a new reality from a lower level, this is at the heart of statistical mechanics, and it's actually still a very active field of research. And it's connected to what is known as the renormalization group. And I'm just like throwing out a name, just a word there. I'm not going to go into that. So the idea of more is different. The way that David Tong says is that 10 to the power 23 is not equal to 1. Okay, so what are we going to do is that we are going to apply statistical ideas to microscopic laws. So we are going to apply statistical ideas of averages, probability, stuff like that, to microscopic laws. Sometimes just microscopic, just these laws are very crude ideas. We don't even have to be very, very specific. And these microscopic laws can be classical or quantum, or as I like to say, quantal. You know, so for example, one can derive the macroscopic laws such as the ideal gas law. And I think this is something that you have seen. So the ideal gas law is derived from a classical picture of gases, right? So that's an application of statistical mechanics. Another one is the, the Dulong-Petit, formula for specific heat for solids, or specific heat capacity for solids. Have you guys seen that in your thermodynamics course or thermophysics course?
No, sir.
Okay, so that's something we'll cover, hopefully. And then there's also the famous Stefan Boltzmann law. The Stefan Boltzmann law is, so Stefan and Boltzmann are two people. This was about how, when you heat up a solid, what is the radiation flux that is given out by hot solids. That's the Stefan Boltzmann law. And when you read, when you study, especially in quantum mechanics, one of the foundational experiments that led to quantum mechanics was the black body radiation, and Stefan Boltzmann law is part of that description. And then, for example, the magnetization, demagnetization of ferromagnets is given by Curie's law. So all of these are examples of statistical mechanics. Some of them are application of statistical ideas to classical physics, microscopic physics, and others are examples of application to statistical ideas to quantum physics, okay? So statistical mechanics is extremely important, and historically it has been very important. So historically, stat mech has been very important in physics, and it continues to be. So for example, the application of statistical mechanics to the problem of radiation led to the birth of quantum mechanics. Okay, so the founders of quantum mechanics, Max Planck, he was an expert statistical mechanics person. And he solved the problem of the black body radiation if you use classical statistical mechanics to derive how much energy a black body is going to radiate when it's heated up. Classical statistical mechanics gives you the wrong answer. Classical statistical mechanics tells you that you should get infinite amount of energy out of the black body. This was known as ultraviolet catastrophe, because if you look at the radiation that is being given out and the wave and the frequency of the radiation, then the curve that is observed is something like this. But classical statistical mechanics, it was quite accurate at the bottom of the curve, but sorry, this is not a good drawing, but it gave you infinite results as you went up in frequency. And Planck realized that if he assumed that the oscillators, which approximates the molecules on the body of the black body, if their energy levels were quantized, if their energy levels were given by some integer times h bar omega, h bar is Planck's constant, omega is their angular frequency, then this curve actually, it gives you the observed curve, okay? It was something that he assumed without any justification. So he assumed it, he introduced it by fiat, but he was able to figure out the curve. And then that opened up the door for quantum mechanics. Okay, so this is kind of a qualitative introduction. So before I go to more quantitative stuff, does anyone have any questions? Okay, somebody asked a question. The question is, for 3 or more objects, will chaos come into any quantum effects? Okay, so that's an interesting question. So we know that classically, the 3-body problem in gravitational physics, for example, is a chaotic system. And this was famously discovered by Poincaré. So what Poincaré found is that if you have, say, 3 astronomical bodies, and they are, say, of comparable masses, they don't have to be, but I think having comparable masses makes it more obvious. For generic initial conditions, their motion will be chaotic. Now, the idea is that does that happen in quantum mechanics? So there's a short answer and there's a long answer. The short answer is no, but the long answer is the idea of chaos in quantum mechanics is not an obvious extension of the classical idea. There are several generalizations of the idea of chaos in quantum mechanics. And so, for example, let me give you an example is that suppose you have a stadium billiard. So what is a stadium billiard? A stadium billiard is a billiard that looks like a stadium, okay? So this is a stadium billiard. So the stadium billiard, what it happens is that if you have a billiard ball, and suppose that the billiard has it's a frictionless, there is no friction, there is no, there's rolling friction, but there is no sliding friction. Or is the other way around? Oh, there is sliding friction, but there's no rolling friction, so that, and if you hit this ball, if the sides of the billiard, of the billiard table is curved in a stadium shape, it turns out that it's a chaotic system. So what does that mean? What it means is that a slight change in the initial conditions will, lead to a very dramatic change in the final configuration. So that's basically what it means by chaos. Now, the thing about quantum mechanics is that how do you generalize to quantum mechanics? So first of all, in quantum mechanics, particles don't have trajectories, right? So particles don't have trajectories. So for example, so it's hard to generalize this to a quantum mechanical system. So they have to talk about, what are the solutions to the Schrodinger equation when your system has a stadium kind of billiard kind of, shape, and you go from there. So this is kind of just like a segue to tell you that, the idea of chaos, that we understand in classical mechanics, is not something that can be easily generalized to quantum mechanics. That is not to say that there is no chaos in quantum mechanics. There is, but it is not a clear, generalization of the classical ideas of chaos. And it is an active field of research, and there are ideas. How do you measure quantum chaos? And there are ideas such as you have to measure what is known as out of time ordered correlators and stuff like that. So anyway, so this will take us quite beyond this course, but the simple answer is that yes, there is chaos, but the chaos is not of the same nature as classical chaos. Okay, any more questions?
Sir, as far as I know, the classical chaos is because we don't have accurate understanding of the exact initial conditions, but the uncertainty in quantum mechanics is of like a different origin. So I suppose they're not commensurate ideas, right?
Exactly, they are not the same ideas, yeah. But the chaos in quantum mechanics doesn't have to do with the quantum uncertainty. Okay. So chaos in quantum mechanics is a lot more tricky idea. And it's not something it's actually something quite like people are working on it right now. It's quite an active field of research, and I have written some papers on it, but I'm not sure I understand it. Like my last few papers were basically on something to do with, had some aspects of it where it had to do with quantum chaos. And basically what we did is that we just, we measured this quantity. The idea is that in classical, a very good way of defining classical chaos is that suppose you have a system and this is the phase space of your system. So the phase space, if you have 2 points which are very close together and you evolve them under Hamiltonian, then if in some finite amount of time, these two trajectories, diverge quite exponentially, that's where we have chaos. Okay, so this is the idea. Whereas, so in quantum mechanics, we have something called the out-of-time correlator, and it is some string of operators at different time. And if they express some behavior where you have this sort of exponential sort of, divergence, then we say that, okay, that system is chaotic. And so this is something called the Lyapunov exponent. So there are some formal analogies. Okay. All right, so shall we carry on? Because this is more of like a segue. So, I mean, these are very good questions, but, it's just like not possible to say something meaningful without going into a lot of detail. And but in classical mechanics, you have like trajectories which are well defined. For example, in the phase space, these trajectories are well defined, whereas quantum mechanics, they are not. Even the idea of phase space is problematic in quantum mechanics.